Hello and welcome to another episode of Curiosity Labs Between Two Nerds, where clearly we are still in isolation, but we're determined to keep going with our content and give you something to watch and listen to every week. You may, if you've seen us before, recognise our small human beings. We've got them back. We enjoy a conversation with them clearly, or they're available. It's one of the two. And I shall ask them, exactly, I'll ask them to once again introduce themselves, and I shall begin with...
Hi, I'm Athena.
Okay.
And I am...
Oh, dear. How old are you, Athena? You might have aged
I'm
since
11.
the last episode. Perfect. And the other one?
I'm Raafae. I'm Raafae, and I'm also... I'm also 11.
Oh, right, this is going out without a glitch.
Smooth.
Right, and you know the nerds, I am Mo.
And I'm Eugene.
Who's back?
Yes, he is. Missed an episode.
Yeah. All right. So we thought today we'd stick with the big topics. We did quantum mechanics, an overview of quantum mechanics last week. So I thought we'd go stick to another big, huge concept, which is relativity, right? And why don't we actually throw it away to the kids? Throw it to the kids to explain relativity. Right? Go on, Athena. What's relativity?
So relativity is this concept that Albert Einstein developed, and there's more than one type of relativity, right?
Yeah, go ahead.
And I don't really know too much about it.
Yeah.
Hand over to Raafae.
Yeah. So
Yeah,
Raafae.
but
so I think relativity's got something to do with perspective from to moving objects, because when I learned about it in my science at school, it said that if you have two trains going in opposite directions, then in the perspective of one train, the other train would be going, if they're going at the same speed, twice as fast.
Yeah, so that's basic I think that's Galilean relativity or something. So there's been the original theory of relativity was, I think, by Galileo, which is what Raafae is talking about there. Nowadays, when we say relativity, we mean the Einstein, the cool one, right? But I mean, they're both really cool. So like the Galileo, so what you were saying with that relativity, like let's say you're in a car and your car is moving along the road at 100 kilometers per hour. And on the other lane, the other side, there's another car coming towards you at 100 kilometers per hour. So actually, if there's a car stood still, right? So you are, or let's take something that would stand still, like let's say a lamppost. Those, even though the car is moving at 100 kilometers per hour, it looks like the lamppost is moving towards you at 100 kilometers per hour, right? It is actually, it's relative to where you're taking that measurement, right? And there's cool things about this, like if you're in the car and let's say you're on a train, 100 kilometers per hour, you're at the front of the train and you threw a ball out in front of you at, I don't know, what, another 100 kilometers per hour. Now that ball that you threw is traveling.
Big throw. A big throw.
100 kilometers. I mean, yeah, this is like Major League Baseball pitching, right? That's like 99 miles per hour. So, okay, that's what I can do. I don't know about you.
Give me a bat.
Yeah, so then that ball now, those speeds add up because they're in the same direction. So that ball is actually moving at 200 kilometers per hour relative to a stationary object, right? Or even if you're playing with that ball on the train, well, you don't, relative to you, that ball looks like you're just throwing it up and down, but actually relative to someone outside the train, that ball is moving up and down, but it's also moving along at that 100 kilometers per hour. Yeah? That's it so far? Yeah?
Yeah.
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 A super simple one. Now, this isn't to do with Einstein's general relativity, but just what the word relative means is to ask if you're tall. So, am I tall? Now, I would answer that yes, because I'm tall relative
To
to an
Mo.
average. To Mo, yeah. So relative to Mo, I am tall. But you can ask me that question, and the answer could be yes, or could be no, or could be average, because relative to Mo, I'm incredibly tall. But relative to an NBA basketball player, I'm not tall. So to answer the question, you have to have it in relation to something else. So in the examples Mo was giving, it's in relation to a stationary object on planet Earth.
Yeah.
So always there has to be a point of reference. Otherwise, it's nigh on impossible to give an answer.
Yeah, it's also, you know, someone asks you, like, I used to get asked, oh, is pizza healthy? I'm like, okay, compared to what? Right?
Yeah.
I mean, you have to give me more information. If it's someone who hasn't eaten in like 3 days, yeah, pizza's pretty healthy then, right? It says relative, it always depends on what you're comparing it to. So how do we go from there to Einstein's mind-hurting relativity? Well, okay, do you guys know any of the strange consequences of his theory of relativity? Either one?
No.
No?
No.
No? All right. Oh, this is easy.
Good.
Okay. So, I mean, okay, so there's, I guess before 1905, which is when Einstein came up with the first theory of relativity, which is special relativity, there was this notion from, you know, we were talking about Newtonian mechanics, right?
Right?
There was a thing in that where of absolute space and time, which basically means that 1 meter, let's just say for space, we measure it in meters, right? 1 meter is always 1 meter.
Mhm.
Okay. And 1 second is how we measure. So we measure time in seconds, is always 1 second.
Right.
So you could say it in a way like it's time moves forward in 1 second per second or something like that, some tautology there. But yeah, so there was this notion of absolute space and time. And then Einstein's special theory of relativity comes along and says, like, no, there's no absolute space or absolute time. Right. And it's actually, so I think it's there's an experiment. So okay, you know, light being the fastest thing in the universe, right?
Yeah.
Actually, that's one of the things that comes out of this formula. Actually, what Einstein says is that there's a universal speed limit, okay? And nothing can go faster than this speed, which you write as c. And that also is the speed of light in a vacuum, which is around 300,000 kilometers per second. All right. It's not saying that light only is the fastest thing in the universe. There can be other things that move at that speed, but that's just the top speed. All right. And I think there were these experiments that people were trying to do. That's always amazing. You know, when you're even talking about quantum mechanics, right? It's amazing the kinds of experiments people set up, how their curiosity took them to those places to set up these insanely precise and tedious experiments to discover all of these things that form the basis of relativity and quantum mechanics. I think one of them was they were trying to measure, okay, no, they'd measured the speed of light. They knew what light, how fast light was, but they thought that light, like, you know, if you have any kind of wave, you need a medium for the waves to travel in. Right. So if you have, like, on the beach, you see waves, the medium there is water. Right now with sound that you can hear, right? That medium is traveling through air. That's why if there was no air, you wouldn't hear anything. And even with light, they thought that light needs a medium to travel through. And they said that this medium was called the ether. And they were trying to measure, so it was a theorized, and then they were trying to do experiments to prove its existence. And I think one of the things that So there's a famous Michelson-Morley experiment. So what they did was they wanted to see whether there was a difference in the speed of light at different parts of our orbit. So, so the Earth is going around the sun, right? Now, let's say if you measure light coming from the sun as the Earth is orbiting in the same path as that light, right? Then surely, right? So because you're moving away, that the light would come to you a little bit slower, right? And if you're moving into the light, it would appear that the light's coming at you faster. And if you're going perpendicular, you guys know what perpendicular means, right?
Right.
Mhm.
Yeah, at a right angle. Yeah, then it should be
Yes.
the exact same speed. So they were trying to see if there was that difference in speeds depending on where you are in Earth's orbit around, where you are in reference to the Earth's orbit, right? And then what they realized when they did this experiment that there was no difference. And they devised this amazing experiment where they split like a beam of light down two mirrors, like half silvered mirrors, and they formed them back together. And they were looking at, it's crazy, right? And but they found that there was no difference. It didn't matter which direction you were moving in, light always had that same speed, right? Now that's
Mhm.
weird because how we were talking
That's
about
properly weird.
yeah, because okay, so if we bring this down to if we take it in an example that we can get our head around, let's
Walking
say
towards a torch.
or let's put yourself on a train, right? And you're on this train moving at, let's say, 100 kilometers per hour. Okay. Oh, let's make it have the same units. Let's say 100 kilometers per second. It's a really, really fast train. Okay. Right. And you shine a light, or you fire a laser beam or something in the direction, like you're at the front of the train, you fire it along the same direction that the train is traveling. All right. And if you have someone else measuring that beam of light that reaches them, now because the light beam is moving at 300,000 kilometers per second, and the train is moving at 100 kilometers per second, then surely the light would reach that person at 300,000 and
400. Yeah, well, you
300,000.
made the train faster, so you made the train 100,000, so it should be
I said
400,000.
100 kilometers per hour. Didn't I?
You went super fast.
No, I said I
came up
have
with
from
a
100
ridiculous
kilometers
train.
per hour to 100 kilometers per second. I thought that's what I said, but all right. So I said,
okay, yeah, maybe.
So 300,100 kilometers per second, right? Because you add the speeds on. It's like with the ball and you're throwing the ball off the train. But it turns out that when you measure that beam of light, it's still moving at c. Okay, we should just say c, right? It's moving at the speed of light. And if you did the opposite way, though, right? So you shoot that laser beam in the opposite direction to travel. So you should minus the train speed. So it should be c minus 100, but actually it's still c. So no matter which direction, it doesn't matter, right? Light, that speed of light doesn't change.
Mhm.
What do you think of that?
Because if you're measuring it relative to the train, then it would be
We're not measuring it
slower
relative to the train. We're measuring
but
it
if you're
to a
normally
stationary
from
person.
yeah,
Yeah.
but if you're on the train, then it would look like it's still going faster than the train, but not as fast. I'm confused.
Yeah. So it's moving. So basically, the thing like we did with the ball, we throw the ball, and you're adding the speed of the train and the ball, right? That doesn't apply to light. With light, it's always the speed of light in whichever medium it's moving in. And the only way, just to simplify it, if we don't have to get into the math, right? The only way that makes sense, if that's the case, is that other things have to change. If the speed of light doesn't change, right? Now you're measuring speed in terms of distance divided by time. So those two factors there, the distance, that the space you're traveling in, right, and the time it takes have to change instead. And that means now distance, space, and time are no longer absolute. That means that they are also relative to the speed of light.
Mm-hmm.
Okay. So one of the things to make that math make sense, you have to space shrinks. Okay. So let's say a train, that this train is moving at 100 kilometers per second. Let's say if it was stood still, right? It measures, I don't know, 100. What's a unit to use? Let's say it measures, I was going to say 100 kilometers. That seems ridiculous. 100 meters? Is that one carriage? Yeah, or something? I don't know.
Yeah.
Let's say it measured 100 meters stood still, right? Stationary. But once it starts moving at 100 kilometers per second, if you could somehow measure it from that same stationary reference frame, right? It would be shorter. It wouldn't be 100 meters anymore. It might be, I don't know, do the math, but maybe like 90 meters or something. So things shrink as they move faster.
But not actually.
No. I mean, not actually. They shrink.
That's why I should run.
Yeah, that's why exercise works. No, but it actually shrinks. Not to the people on the train. On the train still feels like 100 meters, though. Okay? But if you were to measure it from another frame of reference, like a stationary frame of reference, it's shrunk now. That's weird, right? So for particles, let's say a particle is moving near the speed of light and it has to travel light years, right? That distance that it's actually traveling, those light years, to it doesn't feel like light years. For it, it's actually that space it's traveling through shrinks. It's not for it, it's still moving that distance, but that space is shrunk now. So that's one thing. So absolute space is out the window, right? But another weird thing, which is probably even weirder, okay, is that what about time? Like if space isn't absolute, then neither is time. Like it's not absolute either. So let's say,
So if we start with the story, that normally on these stories bubbles get burst, but I think this is recent enough to probably be true. So Einstein was doing his boring day job.
Yeah.
And then he'd get the tram home, and whenever he wasn't doing his boring day job, he'd be thinking like Einstein does, which would be an amazing place to be, a sort of fly on the mind.
Yeah.
And his tram is taking him home, and it's moving away from the big town clock. It had a name, but I don't care what it was, but he's moving away from a clock. So he's thinking, if I started moving away, if this tram accelerated and got closer and closer and closer to the speed of light, and he carried on looking at that clock, once he hit the speed of light, that clock would stop. So time for him, and this is what started really getting him thinking, time for him had changed relative to the person that was stood at the clock. So time for him has slowed down enormously. So he is traveling through his time is different to the person that remained at the clock. Yeah. He's going much slower through time. So he's literally traveling through time.
Is that why if you, in them movies where you fly around the earth loads of times and then you come back and everything's really old?
Superman.
Yeah. Yeah, that is one of the things. So the faster you're moving, the slower time moves for you relative to someone who isn't moving that quickly. So all right, let's say me and Eugene here, you guys are about 20, 30 years younger than us, right? Me and Eugene, we're amazing Curiosity Lab science teachers. Secretly during this lockdown, we built this rocket that can go close to the speed of light.
I thought we weren't going to talk about that.
Oh, sorry. It's not like anyone's listening to this. So, right? So what if we get into that rocket, right? And we go for a year-long trip, okay, close to the speed of light. Now, for another reason, we can't actually travel at the speed of light. But let's say we go at 90% the speed of light, or some appropriate speed to make this next bit work, right? So when we came back after a year, right? Okay, so we have been traveling. We've been marking in our rocket. We've been marking the days down, right? Okay, so a year from the 4th of April, the 4th of April, the 30th of April, when we're recording this, right? We say we'll be back 2021, April 30th, right? But when we come back, if we went at just this right speed, which we could calculate, we could arrive back in the year 2040. So you two would be about the same age as me and Eugene.
How cool would that be?
and we would just be a year older, though. Okay. Here's a bit to remember: we haven't aged as much. We would, all four of us, would be in the same ballpark, in our 30s to 40s. Eugene.
Yeah, I'll take that. I'll take that.
Okay.
It's a good ballpark.
So there you go. So just by moving quick enough, we have made it. It's kind of like we have moved. I think with Athena, we talked with you about this, about time travel and moving at different speeds, right? So we've all come back. We've all moved moved into the future at different rates. Mm. And we'd all be the same age-ish. How is that?
I don't want to picture that.
So we're going to do that?
Yeah, now how does that sound?
I don't want to picture it.
A bit crazy? Yeah? Why?
It's just not right. It's just, no.
But here's the
Do you know there's another famous thought experiment of Einstein? It's to do with time dilation, which is in the same ballpark. So, and I'll change his. You may have heard this before, but I'll sort of take the same thought experiment but change it slightly. So, we're on planet Earth, and let's say 1,000 light years in one direction, there's a star, and 1,000 light years in the other direction, there's a star. And both of those stars go supernova for us exactly the same time. So in one moment, you're looking at the night sky, and way out to the east, there's a supernova, and way out to the west, there's a supernova. Now that light's taken 1,000 years to get there, but for us, it's happened at exactly the same moment. Now, if you go let's take a 30-degree angle from one of the stars, doesn't matter which one. Let's say we go to the star to the east, take a 30-degree angle or something and go another 1,000 light years away, and there's another planet. Now that planet can also see both stars. So now I'm stood on that planet. Those supernovas that happen for you in the same moment, for me, there's going to be you can work out the hypotenuse of the triangle that you've created with the two stars and my new planet. So I might see one. So you see them in exactly the same time. I'll see the first supernova, but it might be another 1,300 years before I see the second supernova. Yeah. So for something that for you has happened in that same instance, in that moment, for me, I'd have to wait 1,200 years to see them both. So you would kind of know my future. You would know that I am going to see what I'm going to see in 1,200 years. But you could only tell me if you could travel at the speed of light.
Yeah.
Which would be cool if you can do that.
Yeah, but unfortunately, one of the things with this is that you can't travel at the speed of light. You can get close, but you can't reach it. As long as you have mass, you can't reach the speed of light. Right? So only massless particles, like photons, right? Or only they can travel at the speed of light. And anything with a mass, I think even, I guess, electrons, right? They can only get close. So they can, the Large Hadron Collider in LHC in Switzerland.
I recognize the name.
Yeah.
CERN.
Have you heard of CERN? So it's a particle accelerator underneath the ground in Switzerland, right? They have this tunnels where they use electromagnets and they accelerate these particles close to close to the speed of light. I think they've got it up to like 99.99999% the speed of light, but they can't go that extra 0.00001 because that's just not allowed, right? Because to go ever faster, you need more energy. And if you actually have to reach the speed of light, you would need an infinite amount of energy. You need you would need more than, I guess, all the energy in the universe to make that happen, right? So it's impossible for anything with mass to reach the speed of light. You can get close, but not see. Okay? Yeah, but
so we can still do the thing where you end up the same age as us. That's achievable.
I'm getting like serious deja vu of like all these movies I've watched.
Yeah, there's truth to it. Now, actually, so this is special relativity, and in general relativity, this is where Einstein actually realized that space and time itself are curved. Okay, and it's not just around moving at the speed of light that can make space and that where you can see this relativity in space and in time, but also around huge amounts of gravity. Gravity can also have an effect on space and time. So that's why around black holes and things, because there's so much gravity, you have lots of the same things happening. So if you were to fall into a black hole, we talk about spaghettification and I guess having to dodge that accretion disk and all of that stuff along the way. But because there's so much gravity as you're falling in, it's like time is stretching out for eternity for you. So it's like time is kind of like at a standstill. So it's hard to get the language right here, but it's like, so your whole future is just out in front of you. It's just kind of like you're frozen in this time. Right? Of you falling into the black hole.
So you don't actually go into the black hole because you're not doing anything because time's frozen, but you actually are doing something because you fell into a black hole.
It's just time feels, I don't know actually. Time stops for all intents and purposes. It just stretches out. But I mean, for you, it's fine. But for someone observing this from the outside, though, it looks like this moment is frozen.
Have you seen Interstellar?
Oh, I love that part.
I don't know if you're old enough to see Interstellar. I have no idea what the rating is. If you haven't watched Interstellar, watch Interstellar, which is an amazing film. And there, well, obviously it's a movie, so there's lots of not likely to happen in there. They've got the science really, really accurate. So there's a part, so we were talking about flying in a rocket. We'd need to go to close to the speed of sound. Well, mass can do the same thing. So I can't remember the scene or who was in it, but these guys land on a planet and the planet has got so much mass that time is much, much, much slower on that planet. So the same as let's fly in a space rocket at the speed of light. If you go somewhere with an enormous amount of mass, your time will move differently. So these guys go down to the planet, leave their mate in a spaceship, not on the planet. They're there for, I can't remember the movie, but let's say a couple of hours.
I've seen it.
We'll go with that.
Yeah, it was 2 hours.
2 hours. So they're there for 2 hours. They then go back to their spaceship and meet their mate. And their mate, I think, has been on there for 23 years or something.
Yeah.
So time, and that, scientifically speaking, is absolutely accurate. That can happen and that would happen. So that's much more achievable, probably, than, although you landing on a planet with that much gravity does come with its own issues. But if you could travel effectively backwards in time. But you'd only be backwards in time by the time you're forwards in time. Yeah. So when you went back to your mate, they've lived another 20 years and you've lived for 2 hours. And that's all just because the amount of mass is creating this huge curvature of, like we talked about with gravity, this huge curvature of space-time itself.
Yeah. So what, do you guys believe all of this? Or you think we're just making it up now?
No, it sounds feasible.
It sounds made up.
It sounds made up. Well, everything's
Does this
made
Sounds
up.
made up. I mean, I've heard some of it before, so I mean, I'm pretty sure it's not made up, but it kind
I
of
don't
sounds
know.
like it is some parts.
But you know what? We can
Listen.
actually test this. And there's lots of things that we depend on nowadays, right? That if it wasn't true, right, these things wouldn't work. Like GPS, I was gonna say GPS satellites, but the satellites for for GPS, right? So your Google Maps wouldn't work because those satellites orbiting the Earth, they're moving at a faster speed, right, around the Earth. So for them, time is moving slower than it is for us. So you have to correct for this. So the way it works, we send a signal up to the satellite, the signal gets beamed back down, and then your app or the software, whatever, it's calculating the difference there. And it has to factor in for the changes in time there, the differences in time. Okay? So if it doesn't correct that, the GPS would be way out. Like right now, it's incredibly accurate, like within 10 meters, even 2 meters, right? But if it wasn't true, right? If it wasn't correct, then all of this, like GPS for one thing, wouldn't work as well. But it's true.
It's a flat Earth and space is fake anyway, so it doesn't really matter.
Oh, space is fake. Did you guys see that? I think, was this recently? There was that black hole popping out of another black hole's accretion disk. I think I read this somewhere yesterday. So there's a huge black hole. I mean, I'm like thousands of times bigger or millions of times more massive than the sun with a huge accretion disk around it, right?
What's an accretion disk?
Good question. It's like when you around a black hole, because there's so much gravity, right? You have loads of things orbiting the black hole outside the event horizon. The event horizon is the actual black hole part. But even where once you enter that, not even light can escape. But around that, you have gravity, right? There's still strong gravity around it. So you have these things orbiting the black hole at tremendous speeds. And they're all like, they could be like just dust floating around in space. And there's all this friction of all this stuff rubbing around it. So they get hot, like, you know, the black body radiation stuff we talked about, right? Because of the speed and the friction. So they're giving off light. So around some black holes, I don't know about all, but you will find this glowing ring of stuff. So it's called the accretion disk. And this black hole that they were talking about is massive. I'm hoping this wasn't in some dream or something. I vaguely remember this. I'm sure this is real. I mean, in lockdown, things are just like all over the place. I'm reading so much news.
I want to hear the end of this.
Okay, but anyway, I swear this
another black hole popped out and waved hello. Did it
but there was a smaller black hole, right, which is about 150 times as massive as the sun.
Guys are all frozen.
You're frozen, Athena.
Yeah,
I think you're back.
You're back.
So there's this giant black hole with something like 1,000 to 1 billion solar masses. Okay.
Wow, you're giving yourself some range there.
Yeah, because I'm sure it was 1 billion or 1 million, right? Okay.
So it's either 1,000, 1 million, or 1 billion.
I'm sure it's correct. I could actually Google this right now, but let me finish the story before we find out whether it's true or not. And then, but in that accretion disk, you had another black hole that's orbiting this one, which is 150 times the mass of this black hole, and it's popping like every. So you can see it becoming. You can't see it, but it brightens up the region of the accretion disk around it, right? So it's like, I'm sure this is real. Okay.
That's cool. Do you think it's on its way in, or it'll get spat out?
I don't know. I even remember they drew like they showed you the orbit, and it's making like this at a 10 to 12 year like period of this orbit that it's orbiting the other black hole. I'm actually Googling this. black holes.
The
Orbits.
dream monkeys in your mind. Well, it makes sense they do. There's black holes everywhere.
Yeah. Okay, this is a real story. Thank God. Two black holes dancing with each other.
Oh,
Oh,
wow.
see, that's much more poetic than how you've put it.
All right. Yeah. One is 150 million times the mass of the sun, and there's 100. Oh, yes, they're big. Look it up. Anyway,
We'll Google that.
yeah, back to relativity. So it sounds made up, right? But it's not. But by the way, so the one of the things that is fixed about the universe, so space and time aren't fixed, but this speed limit, that is fixed. Okay. And the only reason like we can't notice any of this relativistic strangeness is because we're not moving anywhere close to the speed of light. Once you start doing, you have to draw, there's space-time graphs that you draw. You know how we draw one with the X and Y axis, right? So there's space-time graphs where you put all of space on the X axis, okay? And on the Y axis, you've got time. And then you draw these things called light cones, which move out from a certain path. So at the speed that we are moving at, these two light cones into the future and into the past are kind of like almost parallel to each other. So there is this moment of now, like a thin slice of now between the two and stuff. So anyway, light cones, that's a whole other thing. Yeah.
That's next week, can't wait.
I think I saw something somewhere that said that Einstein believed in white holes.
Did he? But he didn't really believe in black holes, to be honest. Like it was there apparent in his formula, right? But then he never like took it to that conclusion. Even the same thing with the Big Bang. It was other people using his formulas that kind of expanded on it and came up with the Big Bang and black holes as well. Yeah. Athena, anything to add? No.
No.
How much of that made sense?
Most of it. There's a couple of
Really?
parts. Yeah.
Yeah, but just you're moving.
Yeah, on simple terms. So you stick two clocks, one on the ground, one in an aeroplane. You'd need accurate clocks to measure it, but they will, if they're perfectly synchronized, by the time the plane lands, you check them, they won't be synchronized anymore because time will have moved differently. You do the same thing with mass. So if you put one of those clocks next to something supermassive, like a mountain, and the other one not near something supermassive, then that mass will change the way time works, and you bring them back together, and one will have experienced time differently to another. And
really
even
cool.
you walking around, so the more you move, the slower time goes. Now you're not moving anywhere near the speed of light, obviously, but it's scientifically true that if you move, time slows down for you. So if you want to feel like you've lived a long life, just keep moving.
Yeah, in the direction of rotation of the Earth as well, just to give you that extra push.
Give that extra little kick. Yeah. Boy, so that would be west to east. East to west, east to west. Yeah.
Just
never walk west to east. Waste of time.
Yeah. That way you're actually going to do the opposite.
Yeah. Madness. So yeah, while it's the same as I'm looking at my screen at the moment, and the light from my screen is taking time to hit my eyes. So I am looking technically into the past. Now it's infinitesimal, the difference, but it's the same. If you're moving, you're experiencing time slower than someone that sat still, even though that difference is infinitesimal. The science is true. So you scale that up, you get faster and faster and more mass, then it starts to make, you get to the point where you're a black hole and time has stopped.
Yeah.
So the science is awesome.
Yeah, it's really cool.
Yeah, and by the way, this is all still part of Newtonian mechanics, though. This isn't quantum mechanics. So
Okay.
What?
quantum-
Even Newtonian mechanics is confusing.
What?
No, it's not. I mean, this bit, yeah,
Just
it's
stuff.
This
Moves.
is strange, right? But it's true, and it just is, and it's amazing. It's a cool theory, I guess, right? Because it's so these implications of it. They involve time travel and things that we thought that are fixed, that are changing, and all of that. But this is Newtonian mechanics, which in the end, kind of quantum mechanics, right, which we were talking about, supersedes it. So in quantum mechanics, there's like, I don't know, like there's no, relativity is like the best theory that we have for big stuff, right? But then it doesn't really work well with quantum mechanics. And when this only matters when you get to black holes, where you have a black hole is a quantum, it's so small, right? So it's in that kind of a length scale, right? But then it has so much mass. So the mass part keeps it in the Newtonian mechanics scale with relativity. So you have to find, so it's this place where both of them meet and they don't work well with each other. So what is going to end up happening is that we're going to find out that even this Einstein's theory of general relativity isn't the full story. That actually there's something more to this. There's something else to come, right? We don't know what it is. If you'd figured it out, it'd be one of the greatest scientific discoveries, at least of this century, for sure.
I'm going to have a crack this evening.
Yeah. Okay. So, yeah. So this is Newtonian mechanics, and I don't want to say it's wrong. It is right. It's a good approximation.
Oh, don't say it's wrong.
That's not wrong. It's an approximation. They're all approximations so far. No one's got the final theories yet.
But it works. It works. It works in just about everything we look at.
Yep.
It works. And that is kind of evidencing that it's a pretty accurate theory.
Cool.
Cool.
All right, guys. Hope you enjoy that.
Right. Well, thank you. I hope you got through that and clung on as the conversation went on. If you did enjoy that and you haven't already, please do hit that little like button wherever it is on your screen. And if you haven't subscribed, please do so. We will be sticking out new content every week. If you are a regular watcher or listener, thank you very much. We hope you enjoyed, and we shall all now, for those watching on YouTube, wave relentlessly.
Okay, wave. Bye.
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 See you later.
Okay.